So we have in question 4, we have an object released from rest near the surface but above the surface of rest, so V0 equals 0. The object is dropped. Determine the relationship between the direction of the gravitational force and the change in momentum caused by the force. What data would the student to determine the magnitude and direction of the gravitational force and the change in momentum of the object? So the change in momentum is delta P equals m delta V. And if we want to know the magnitude of the gravitational force, we need F equals mg. And we know the direction is downward all the time. So the mass of the object, that is definitely true. We definitely need the mass of the object both for the change in momentum and the force of gravity. So force due to gravity and the velocity of the object the instant before it changes the surface. Right, and so if we know, since delta V, which is what we need, is V minus V0, and we know V0 is 0, then V equals delta V. So if we know delta V, we know that the velocity the instant beforehand, we know the change in velocity. So it looks like choice A is one of our correct answers. And so again, we've already established we need the mass because it is the force due to gravity. And the distance fallen by the object because the force is exerted during the entire falling distance. So if we know the mass, we know g, we find Fg. And if we know the distance, what does that do for us? Well, we know we are looking for delta V, and average velocity is delta z over delta t. So if we know delta z, that is going to be v bar delta t. And if we know the average velocity, which is v plus v0 over 2, v0 is 2, then the final velocity is twice the average velocity. And we've already said that the instantaneous velocity is the change in velocity. So if we know that height, we can find delta z, and that delta z then would allow us to find the average velocity if we know the change in time. But we also know that the distance fallen, delta z, is 1/2 at squared plus v0t. And the v0 is 0, so that drops out. And if we know delta z and we know a, then we have t. And delta t is t, which is delta z over v, over the average velocity. And the average velocity is, so we have delta t is delta z over the average velocity. So we can put that into this equation, 1/2 a, and delta t is t. So delta z, delta z squared all over the average velocity squared. So solving for the average velocity squared, we get v squared equals 1/2 a delta z squared over delta z. So we've got 1/2 a delta z. So knowing the acceleration in delta z, we can find v squared, and if we find the average velocity squared, we can find the average velocity, and the average velocity then is equal to v over 2. Or the final velocity is twice that average velocity. And if we know the average velocity, we know the final velocity, that's delta v. So it's a really long, circuitous way to get to it, but it looks like B is the choice answer. So let's look at choices C and D and see if they might be better. The velocity instant before it reaches the Earth's surface because it's required to determine the change in velocity of the object. So that's a true statement. And the acceleration of the object because it's required to determine the force due to gravity. Well, no, we know that. It's Earth. So that's not something we need to know, and that's why C is out. So we've got distance fallen because the force, the entire distance, and the acceleration of the, so here's the acceleration, we already know that. Determine the force due to gravity on the object. Well, that's true, but we already know that, so D is out.